Hello, my name is Henriette and today I will be talking about biochip technologies. This is an outline of the presentation. First, I will give a short introduction about biomedical devices, then spend the rest of the presentation talking about three main aspects which are the INFET, the MEMS or NEMS, and lab on chips. Finally, I will give a short conclusion about the whole presentation. Biomedical devices have been around for decades. Today's biocircuits provide therapy to treat numerous conditions. The major current trends of biomedical electronics are portability, miniaturization, connectivity, humanization, security, and reliability. Probably for the sake of this presentation, miniaturization is the most important aspect, since it requires advanced integration technologies like CMOS integrated circuits, or heterogeneous integration of CMOS, MEMS, and/or flexible technologies. Semiconductor technology is now being used for early detection and therapy of disease. Low-power CMOS-based systems can be designed to replicate biology to provide implantable and portable devices for personalized therapy of conditions such as diabetes. Genomic advances in CMOS-based INFET technology, for example, is now allowing implementation of point-of-care diagnostic systems. So what is an INFET? The ion-sensitive field effect transistor, INFET, or sometimes referred to as ISFET, is implemented using a standard MOSFET simply by removing the gate metal oxide and exposing the polysilicon to a solution. The result is that the threshold voltage of the device is directly related to the pH of the solution, due to the binding of hydrogen ions, which is in fact due to a combination of arising from the side binding of ions on the insulator surface combined with the formation of a double layer capacitance. An INFET source and drain are constructed as the same way as for a MOSFET. The gate electrode is separated from the channel by a barrier which is sensitive to hydrogen ions and the gap to allow the substance under test to come in contact with the sensitive barrier. An INFET threshold voltage depends on the pH of the substance. So basically, when the ion concentration changes, for this example we have the H plus ion, the current through the transistor will change accordingly. And here the solution is used as the gate electrode. So as you can see from this figure, the threshold voltage of the transistor will change in time as the pH of the solution changes. INFETs are effectively floating gate devices. They suffer from random trapped charges that alter their threshold voltage. To help overcome this, researchers are investigating bidirectional electron tunneling. In order to bring the threshold voltage to a desirable value, using bidirectional electron tunneling, two inputs are capacitively coupled to the INFET floating gate via matched capacitors. They are used to indirectly tunnel opposite currents across their oxide isolation to the INFET floating gate in a controlled way. The floating gate charges are programmed using a balanced combination of these two tunneling currents. As you can see from the figure in the left, it shows an INFET model in CMOS with two inputs coupled to its floating gate. A positive tunneling voltage VT plus coupled via CT plus, and a negative tunneling voltage VT minus, which is coupled through the capacitance CT minus. They are used for bidirectional indirect tunneling. Because tunneling is carried out between poly 1 gate that is shorted to the INFET's floating gate and the substrate diffusion area, current must be prevented from flowing to other substrate areas. Diode isolation and programming protocol are used to make sure this diffusion area always has a reverse bias junction with the surroundings. The figure in the left shows the model of this arrangement, while the figure in the right is a cross-sectional representation, but it's not to scale. This method provides for threshold voltage programming of an INFET in standard CMOS without additional processing steps. It can be used for fast matching of INFET arrays. This method is particularly useful for disposable lab-on-chip application where devices are used only once and hence reliability is not an issue. The ultimate potential of implementation of InFETs in CMOS, however, lies in their ability to scale with semiconductor roadmap according to Moore's law. This will allow having large arrays of multiple InFET in one chip. Given that InFETs are derived from standard MOSFET, we are now seeing this trend increase the number of sensors per microchip, allowing implementation of InFET microarrays, as shown in the figure. More importantly, this scaling has shown particular advantages in the area of DNA sequences, whereby an increasing number of InFET sensors per chip allows for parallel non-optical detection, leading to a faster as well as cheaper method of genome assembly. In fact, in one of the presentations, an InFET chip was presented with 1.2 million sensors capable of sequencing up to 25 million bases in a 2-hour run, which is very impressive. The FinFET process described in class may be used as a basis for development of nanowire-based detector of ions in liquid analytes. The silicon fin that is fixed only to the bottom to the buried oxide layer or the box can be considered as a nanowire. Its conductance can be controlled by potential of the surrounding liquid analyte. The final, the final dual nanowire InFET is shown. Part of the nanowires covered with the dielectric passivation layer are responsible for the series resistance of the nanowire. These devices have always even number of the nanowire channels connected in parallel. Multiplication of the nanowires allows for significant enhancement of device current efficiency and sensor ability. The developed nanowire InFET device may be used in sensor applications, where a small amount of analyte is required. Moreover, this size is compatible with the biological object scale, so it seems to be promising from biological sample investigation perspective. Chips containing several nanowire devices have been assembled in gold-covered PCB foil. Ultra-compressed bonds and all edges of the chip have been electrically insulated. It exhibits rather low transconductance, which, although not well understood, does not hinder its use in pH measurement application. The output signal hysteresis and short-time stability remain in the range of typical for silicon InFETs with the nitrate dielectric. This kind of devices, they are still in the lab right now, and hopefully soon they're gonna be out for production. So now let's talk about the MEMS. The MEMS stands for Micro Electromechanical Systems, which is an integration of small CMOS chips into a large area substrate. The unique feature of this technique enables the integration of macro-scale components such as leads and microfluidics. A key component of the technique is the CMOS chip-based self-aligned masking. This allows for the fabrication of sockets in wafer that are at most 5 micrometer larger than chip on each side. The chip and the large area substrate are bonded into a carrier such that the top surface of the two components are flush. The challenge in fabricating the MEMS lies in the packaging. The technology now shares similar protocol for the integration of chips. However, none of the proposed technologies offer the best combination of microfluidic integration and post-CMOS packaging of CMOS circuitry. Also, these technologies can suffer from low yield, poor die-to-die alignment accuracy, and lack of robustness. Thus, a new technology has been proposed, which is the versatile chip-specific integration technology known as VCSIT, which is a CMOS, MEMS, and biocompatible and offer both robustness and very accurate alignment. The first step in this packaging technique is the chip-specific cavity, where the chip is embedded in edge cavities barrier in the carrier substrate, as you can see from this figure. The second part of the implementation process involves bonding the chip and the holder onto a carrier wafer. The carrier provides strong support to the packaged chip. Adhesive bonding is chosen for the bonding of holder and the chip into the carrier. Then in part C, which is the gap filling and planarization, in this part of the integration, the top surface of the chip and the holder are planarized in order to have a seamless transition from the chip to the holder. This is a crucial for the subsequent process steps, and any discontinuity at the chip holder interface will lead to a broken metal line and thus an open circuit. As you can see from this figure, the gap between the chip and the holder is completely filled with SOG or spin-on glass. The next step of this process is spin-on glass packaging. This results in a complete gap filling from the backside and planarization of the bottom surface. The SOG film coated on top and the bottom is found to be strong enough to hold the chip firmly inside the holder wafer during any subsequent process step. And finally, the last step is contact pattern. This figure shows the final product of the MEMS. Various biosensing experiments are currently underway utilizing the proposed VCSIT technique for fabricating the MEMS. The VCSIT process can be easily extended to integrate multiple arrays. An alternate way of packaging MEMS is to encapsulate each individual die into the body. The results of this method indicate the post-CMOS process flow developed for packaging implantable dies effectively prevents diffusion of copper or any other metal through the passivation layer, which was an issue for implant devices because it activates the foreign body response once induced in the human body. Before NEMS, which stands for Nano Electromechanical System, devices can actually be implemented, reasonable integrations of carbon-based products must be created. The focus is currently shifting from experimental work toward practical application and device structures that will implement and profit from the use of carbon nanotubes. At this point in NEMS research, there is a general understanding of the properties of carbon nanotube and graphene. The next challenge to overcome involves understanding all of the properties of these carbon-based tools and using the properties to make efficient and durable NEMS with low failure rates. From MEMS, lab-on-chip is becoming very popular and feasible, where a person can perform most of the laboratory tests from home in an individual chip. But some researchers aim to take the NEMS, and the lab-on-chip technology one step further by introducing the concept of a lab on a transistor. In this methodology, laboratory operations are performed individually on a single chip transistor instead of an entire microchip. To demonstrate this concept, a group has developed a heating technique that allows transistors to act as electrically addressable individual heating units. They have coupled the transistor heaters with the placement of sub-nanoliter droplets, as you can see from this figure, to create individual heated reaction volumes. Under this configuration, fed devices become highly localized heater sensor hybrids capable of high-speed thermocycling of less than 1 nanoliter reactions with potential for electrical detection of biological analytes. So in conclusion, in this presentation, I presented some examples of how CMOS technology is now being applied in healthcare to provide novel solutions for early detection and therapy of disease, with specific examples of InFET, MEMS, NEMS, and lab-on-chips, which can be used as application in mobile health, genomic technology, and bio-inspired systems. Looking forward, we now expect semiconductor to create a revolution in healthcare in a similar fashion to the mobile phone industry in the early 90s, providing a new wave of intelligent medical devices wirelessly connected to the internet cloud, providing doctors and patients with continuous real-time information and therapy. However, some researchers took it even one step further. The same way we have a whole computer into a single chip, some researchers have now an organ on a chip, which seeks to replicate the function of a human organ on a computer chip. In Harvard University case, for example, they have now created a living lung on a chip, a heart on a chip, and most recently a gut on a chip and it's in the testing now, which is very, very impressive. Thank you for watching this presentation. I hope you enjoyed it. And this is the reference of use. Thank you and have a good day.